Hey everybody, it's Keith from Last Call Bar Academy, and I'm here with the group of students, and we're going to talk about how to make deductions on LSAT logic games. So let's begin. Oh, whoops, I'm butchering this. Present. Okay. So what motivated me to make this is that when I struggle with a logic game, and even as a perfect logic game scorer, there are still logic games that stump me occasionally where I want to look at a resource. So when I find a logic game to be difficult and I reach out for a video or an explanation of that logic game, the main source of frustration that I find is that the speaker in the video will say, and therefore, and they'll describe some grand deduction that I didn't see. And therefore, J has to be fifth. And I'm just like, whoa, I didn't catch that. And sure, that unlocks the game. Now I can answer all the questions, but I'm still left with this big gap. How do I find that without the video? How am I supposed to sit down and find that deduction on my own? And so I started thinking about what is my own process for finding deductions and how to supplement that process for the difficult deductions that I was missing. And so here's what I came up with. The first thing that I do is I try to challenge people just to rethink the whole idea of a deduction. This took me a long time, to be perfectly honest. On LR, when the LSAT asks me which of the following can be inferred or which of the following is most strongly supported by the stimulus, and then they give me a paraphrase of one sentence from the stimulus, I used to just kind of shrug my shoulders and say, that's not an inference. All you're doing is repeating information. I mean, it really took me a long time to realize that repackaging something in different language is a form of deduction. It's a way of deducing things from the language, that two things are equivalent to one another. So a paraphrase itself, a paraphrase of a statement or a paraphrase of a rule in a logic game is a deduction. If you can take a complicated statement and say it more simply, you've made progress toward finding the deeper deductions. That's step one. All right, let's just rethink what is a deduction. It doesn't have to be the grand deduction. It can be as simple as, have I simplified the language? Have I simplified the interpretation process of this rule or statement or idea? And on logic games, that usually means creating visual symbols. I'm going to come back to that point again, that symbolizing rules is only helpful if you're reducing the verbal complexity. They have to be visual. Most of my students, when they first come to me, they're not good enough at building visual symbols. And so they continue to go back to the rules themselves and reread the rule. My goal is to build a visual symbol of the rule that is so robust that I never want to look back at the language of the rule again. I want to eliminate the verbal complexity of the rule by building a terrific symbol. All right, the other thing is paraphrasing often involves looking at the opposite side of a coin. If you tell me something is true, what does that imply is false? Or if you tell me something is false, what does that imply is true? Sort of like the contrapositive of a conditional statement. Can we take affirmative statements and figure out their negative deductions or vice versa? All right, number two bullet point here is that my original conception of a deduction was that we have to be sure, we have to get down to some concrete knowledge. One variable is locked into one spot. I've abandoned that idea of a deduction, and my idea of a deduction is much broader now. If we have a range of possibilities that's smaller than the entire universe, that is a deduction. So what I'm talking about here are binary and ternary restrictions. If variables are limited to two or three boxes, that's worth noting. Or if a box is limited to two or three variables, that's worth noting because it's a smaller set than the entire set of variables for the game. You don't have to, if you document it, you don't have to go through the process of deducing which two or three things go there over and over again. You just write it down and keep track of it. And then finally, the last thing that we can describe as a deduction is the deep deduction, the frustrating thing that the explanation videos identify that I don't always identify. It's the implicit information that's buried beneath the rules. If you combine them all together and you truly understood all their implications, there would be another set of rules, not different from the existing rules, different ways of describing the existing rules and the way they interact together to restrict the solutions to the game. So we could describe those deductions as buried rules that we have to find. Okay, how do we make deductions? Here's where I've been kind of innovative in creating a step-by-step process that you can use in blind review. Now, one criticism of this process is that it's so laborious, it would be problematic on a time test, would slow you down to such an extent that it might even harm your score rather than help it. So I view this process as a process of conceptual development. It's something that you employ during blind review and during strategy planning. And it's a process that you employ slowly, the same way that you work out with really careful form at the gym. But then when you do the competition, you're trying to do a max bench press, you cheat your form. You don't use the process so rigorously. You hope that the process has built intuitive skills, which you can then employ on the real test. So, what I'm hoping is that if you do these steps diligently on blind review, the deductions will simply occur to you on a time test. I'm not suggesting that you stop and do these things one at a time on a time test. All right, but here's how you learn how to make deductions. Maybe that's what I should have titled um, the slideshow, how to learn how to make deductions. So I start with single rule deductions. And what I mean by that is that I focus on one rule at a time based on the idea that mental multitasking is harmful to my mental deductions. In other words, I'm going to make mistakes if I try to do everything at once. So I do one step at a time, which means focusing on one rule individually before I try to combine them all together. Get all the meat off the bones for each rule before you try to get complex and combine them together. What that means is sometimes I reject my initial symbol. I'll look at the symbol and say, too many words. I can do better. I can make this more visual, and I'll erase it or strike it out and create a better diagram that captures the relationships in a more visual way. Once I have a symbol that I'm happy with, it's either highly visual or I just can't think of a way to make it visual. I have to resort to a verbal articulation. Then I try to tease out deductions by noticing whether the rule gives me positive information or negative. Does it tell me a relationship that is true, that must be true, or something that cannot happen, that can't be true? If the rule is framed in an affirmative way, it tells me this is the relationship. I try to ask myself, well, what are the negative implications of that? What things would be impossible? Where can the variables not go because of that rule? And I document all the negative deductions. If the rule is negative in nature, A does not go here, here, or here, then I do the opposite and I try to identify or notice, well, then what are all the possible placements, the affirmative placements for that particular variable or concept? And it's only after doing that process for each individual rule that I go to step two, which is the multiple rule deductions. Multiple rule deductions involve combining symbols that share a single variable. Two different rules that both discuss the same variable or the same spot in the diagram. And typically, this doesn't work well for negative rules. It works better for affirmative rules so that you can simply combine the symbols together, a physical combination of the symbols by superimposing or overlapping the symbols that they share. And since we're talking about affirmative symbols, once you've built the bigger symbol that encompasses more of the variables, you can tease out more of the negative deductions. I'll show you an example of that in a second. Once I've combined as many rules as possible, well, then steps one and steps two tend to lead to a number of negative deductions that were not explicitly stated in the rules. I end up noting, not B here, not C there, not this, not that. By the time I get to step 3, I have so many of those negations that I can often add them up to go back in the other direction. If I have enough negations about the same box or the same variable, I can flip it around and say, well, if all those things can't be true, then what are the remaining possibilities? What can be true? So it's the ultimate negative to affirmative flip. It's like the multiple rule step 2, but for the negative rules, the negative deductions instead. I add them all up and make one grand affirmative deduction out of them. Those deductions are often binary or ternary. I don't always get down to a single concrete, option. Sometimes there's 2 or 3 options. The final, excuse me, the final step to my deduction process is looking for distribution and frequency deductions. And I'm not going to talk about that much today because that's more of an advanced deduction technique for grouping games. What I want to talk about today is I want to show you an example of steps 1 through 3 as they pertain to an order game. But I'll describe step 4 quickly. The distribution refers to boxes that can contain multiple things. Well, how many things go in the box? That often becomes one of the difficult aspects of a group game. How many things go in group A versus group B? So I keep track of those distributions and the distribution deductions with a symbol. I use slots on the bottom to represent minimum number of things in a group. And then I use some slots at the top to represent maximum numbers if it seems like those are going to be relevant. The other thing that I note, this has to do with the frequency. What if the variables go in multiple times? That's a feature most often found in group games, but you can also find it in some order games, as we saw in class last night. And so when I have repeats, then I want to take note of the outliers. If most of the variables are singles, it's the doubles that I want to, identify which of the variables can be the different one, the outlier, the double. There's other games where all of the variables repeat except for one. And so in that case, the outlier is the single. I want to take note which one can be different from the others. So the slots and outliers distributions, I can do another presentation on that next week if you guys want more information about that. But what I'd like to do is just show you a really simple example of each of these types of deductions. So let's suppose we're dealing with a really simple logic game. This one involves a 5-order sequence, variables A, B, C, D, and E, and we have 3 rules. I'm showing you 2 of them so far. E is before C, B is after C. And so I've shown you how I would symbolize each of those rules using a string or bungee diagram. E-C means E to the left of C in the diagram. C-B means C to the left of B. So what I would do is focus on each of those individually and tease out the deductions. And notice how each of those articulates an affirmative relationship. E is before C. B is after C. So the way to make progress in finding deductions is to say, well, then what can't be the case? If E is before C, then where could E never go? And here's our list of deductions. E could not be fifth because it has to have C after it. C can't be first because it has to have E before it. And then if we do the same thing for rule 2, we can see that C could never be fifth because it has to have B after it. And then B could never be first because it has to have C before it. Those deductions, I think most people find them to be elementary. Of course, E can't be last. It's obvious. But as you're, completing a question, it's not going to be so obvious. And so documenting it now means that you don't have to make that single calculation over and over again. It's frozen. All right, next step, single rule deductions. Let's add a third rule. A is not 1, 2, or 3. You see how I've symbolized that with these negations, not A1, not A2, not A3. I also put the negations above the diagram. I call this a proximity rule. The rules are fine listed off to the side. That's a fair symbol for the rule, but it's not one that's likely to catch my eye while I'm working on a solution in the diagram. So I try to make everything streamlined. If I want to articulate relationships between A and slots 1, 2, and 3, it's best to do it with some proximity to columns 1, 2, and 3. So you notice I added not A, not A, not A up here. And now I can illustrate for you the opposite type of single rule deduction where we take a negated rule. A is not 1, 2, or 3. And we ask ourselves, well, then what are the options for A? And we end up with a binary restriction. A could be fourth or A could be fifth. I could write that A4 or A5. I could use A at the top with an arrow pointing down to either column. When the columns are adjacent to one another, I like to document this type of binary restriction by putting the variable right on the line, because that's where my eye is going to be when I'm thinking about a question. When I get 2-3 minutes from now, when I'm no longer thinking about rule 3, when question number 4 asks me, what happens if we put B fourth? It has to be obvious to me that that impacts A. If it takes me time to go inspect the rules, figure it out, then that's time lost. For efficiency, I want it to be palpable on the diagram that putting something in the fourth or fifth box implicates A. So that's the symbol that I've come up with to represent that binary restriction. It doesn't seem earth shattering, right? You just wrote A on the line. Yeah, but at the critical moment, that's going to get me to the deduction faster than the verbal articulation of the negated rule on the left. Okay, next let's talk about multiple rule deductions. Once I've done each individual rule, I look for rules that share variables. Rules 1 and 2 both share the variable C. So I find that it's better to work with one master diagram that incorporates as many variables as possible instead of individual diagrams for each rule. So I would simply superimpose the two C's to create the sequence E before C before B. When it comes to sequences, most of you probably do this intuitively, but you can do it with conditional statements as well. And you can do it with block clues, and you can combine block clues and string clues to come up with really complex symbols the way we did for the May 2020 Flex uh, order game last night in class. Okay, so where are we? Multiple rule deductions. We're going to go, we combine those together. Now, since we have a larger affirmative symbol, E, then C, then B, it makes certain deductions more obvious. We already knew that E couldn't be fifth, but stringing both C and B into the same diagram makes it more obvious to us that E can't be fourth. And likewise, we already knew that B can't be first, but putting E and C both combined in the same diagram makes it more obvious that B is also locked out of the second box because it has to have two things in front of it. So we can add, based on this combined clue, not B to column 2, not E to column 4. We're starting to build. I told you guys steps 1 and 2, we were going to generate this library of negations. Well, now we have it. So that leads to the next step, the multiple negation deductions. You want to look for multiple negations that apply to the same thing. And we have two examples of it here. We have 3 negations that all apply to box 1. We also have 3 negations that all apply to A. It can't be first, second, or third. We already derived the multiple negation deduction for A. We just did it as a single rule deduction because all of that information was contained in one rule. But the information about A, B, and C, all of that was contained in separate rules. And so now that we've compiled all of those negations in one spot, it's easy to see that we can arrive at a binary deduction for spot 1 in the diagram. It has to be D or E. And I consider that to be a win in two ways. Number one, we had three negations. Now we've reduced it to two options. So we've reduced the complexity of the information that we have to remember or the information that we have to evaluate. The other thing that we've done is we've gone from negative articulations to affirmative. And if I'm right that a negation is a type of abstraction, that means that we've gone from more options to fewer, and we've gone from more abstract to more concrete. So that's a double win. Even though we haven't come to a single resolution, we can pick up the puzzle much further along the logical chain than we would have starting with the three negations. We know every solution has to start with D or E, and that's alternative, but still reasonably concrete. All right, so that's my process for making deductions. I hope you guys find that helpful. I'm going to stop the recording now and then I'll take some questions.